Welcome to Copilot Podcasts. Most formal systems treat Gödel's incompleteness theorem like a stop sign. Here's the wall, here's where math breaks down, move along. But what if someone built a system that treats that fracture as the engine, not the obstacle, the actual power source? Today, we are getting into the KT ontology, specifically its NP hardness proof, type successor propagation, closure set geometry, the hydrogen pivot derivation, and what the paper calls Gödel fracture non-constructibility. By the end of this episode, you will understand what makes this system structurally unusual, why it claims finite AI cannot reproduce it, and what it actually means for a mathematical system to be non-constructible. I've got someone here who has gone deep into this paper, so let's get into it. What is the first thing someone needs to understand about what the KT ontology even is?
So the KT ontology, as described in the paper by Abdon Bishop from the Earth Edge Institute, is a typed generative system. And the word typed is doing a lot of work there. It's not just a set of equations. It's a system where every object, every operation, every geometric structure carries a type label that determines what it can interact with and how it propagates forward.
Okay, so typed in the programming sense almost? Like you can't just mix things arbitrarily?
Exactly that intuition. And the typing comes from something called mod 4 rail typing. The system is built on the odd integers, and every odd integer falls into one of two rails depending on its remainder when divided by 4. If the remainder is 1, it's on what the paper calls the T rail, the tau rail, which carries curvature. If the remainder is 3, it's on the K rail, the kappa rail, which carries torsion.
So kappa is torsion, tau is curvature, and those are the two fundamental rails the whole system runs on.
Right, and the paper is very precise about this. Kappa is the torsion generator, typed by the mod 4 equals 3 rail. Tau is the curvature generator, typed by the mod 4 equals 1 rail. The two rails together form what the paper calls the curvature torsion manifold, and the core geometric object is their product. U of t equals kappa of t times tau of t.
And the whole system is built up from there through what the paper calls a generative chain, right? I saw that phrase a lot.
Yes, and that generative chain is really the spine of the architecture. The paper states it as arithmetic leads to analytic, analytic leads to geometry, geometry leads to physics. Each layer is the typed continuation of the previous one. You start with successor arithmetic on the odd integers, you lift that analytically into complex coordinates, you project geometrically into the curvature torsion manifold, and then you project physically into observable quantities.
Okay, so before we go further, why odd integers specifically? Why not just all integers or rationals or something more familiar?
That's actually answered directly by one of the foundational axioms. Axiom 2.1 in the paper establishes what it calls the rail-typed substrate separation law. The argument is that a Boolean substrate, the 0-1 system, forms what's called a zero-divisor ring, meaning you can have two non-zero elements whose product is 0. And the paper says that any structure built on a Boolean substrate collapses under multiplication and cannot preserve rail-typed successor propagation.
So the Boolean substrate literally breaks the typing system.
Exactly. Whereas the rational substrate forms a field with no zero divisors. If A times B equals 0, then either A or B must be 0. So rational multiplication is generative and preserves rail-typed continuation. That's why the system is built on a substrate where multiplication doesn't collapse.
And there are also these axioms about no true zero and no true infinity. That struck me as unusual.
Yeah, those are axioms 2.3 and 2.4. The paper introduces what it calls a typed microscale element, essentially a smallest admissible scale that is strictly greater than 0. No operator or limit may evaluate at literal 0 scale, and symmetrically, the reciprocal of that microscale is bounded above by a strictly increasing factorial rail, so no curvature, torsion, energy, or analytic quantity may diverge. Both infinities and zeros are axiomatically prohibited.
Which is a pretty radical departure from standard calculus, where limits going to 0 are kind of the whole point.
It is. And the paper is explicit about that in the conclusion. It says the KT ontology replaces calculus with successor arithmetic and diagonal operators. It's not patching calculus, it's replacing the foundation.
Okay, so now I want to get into the NP hardness theorem because that's where things get really interesting. The paper is claiming that generating a KT manifold is NP hard. Walk me through how that proof actually works.
So, theorem 3.1 in the paper proves NP hardness via a polynomial time reduction from AST, the Boolean satisfiability problem. And the paper anchors this to the Cook-Levin theorem from 1971, which established AST as the first NP-complete problem. That's a deliberate choice. It ties the KTT system to one of the oldest and most foundational results in complexity theory.
So the strategy is, if you can reduce SAT to KT generation in polynomial time, and SAT is NP-complete, then KT generation must be at least as hard as SAT, which makes it NP hard.
Exactly right. And here's how the reduction works. You take a Boolean formula in conjunctive normal form, n variables, m clauses. For each variable, you create what the paper calls a curvature dial value, a number near 3.14. If the variable is true, the dial is set to 3.14 plus a small epsilon. If the variable is false, it's 3.14 minus epsilon.
So truth assignments become geometric positions on a dial near pi.
Right. And then for each clause, you create a rail intersection point, a pair of kappa and tau coordinates. The paper defines the typed Gaussian curvature at that point as the product of two curvature contributions, k2 of kappa times k1 of tau complement. And the key encoding is this. A clause is satisfied if and only if the Gaussian curvature at its rail intersection point equals 0.
Wait, so satisfying a logical clause translates to achieving flat geometry at a point in the manifold?
That's the reduction. If at least one literal in the clause is true, then k2 of kappa equals 0, so the product is 0, so the curvature is 0, the geometry is Euclidean at that point. If all literals are false, then k2 of kappa is non-zero, and by axiom 2.5, k1 of tau complement is also non-zero, so the product is non-zero, the geometry is curved. The formula is satisfiable if and only if the configuration extends to a complete KT manifold.
And the construction itself, mapping variables to dial values, clauses to rail intersections, that's polynomial time in n and m.
Polynomial time. Each variable produces one dial value, each clause produces one rail intersection. The paper also notes that verification is polynomial, checking whether C Gauss equals 0 is simple multiplication, and each clause is checked independently in order m time. But the search for the correct dial values requires testing all 2 to the n possible assignments. Search is NP, verify is P.
That's the classic NP structure. And what happens if the formula is unsatisfiable? What does that look like geometrically?
If the formula is unsatisfiable, then for at least one clause, all literals are false, which means the curvature at that rail intersection is non-zero. The geometry is curved there, and the configuration cannot extend to a complete KT manifold. The manifold fails to close. So unsatisfiability maps directly to geometric incompleteness.
That's a genuinely elegant encoding. Logic and geometry are doing the same work simultaneously.
And that's not accidental, it's the whole point of the typed structure. The rails are designed so that logical and geometric properties are isomorphic. Which brings us to the closure set, because that's where the geometry gets its own internal constraint that has nothing to do with satisfiability.
Right. Theorem 5.1. The closure set. What is it and why does it have to exist?
So the closure set is a minimum sampling scale, call it C, below which type successor propagation fails and curvature torsion continuity cannot be maintained. The proof is a contradiction argument. Suppose no such minimum scale exists. Then the vacuum grid, which the paper defines as the set of all rail intersection points, can be refined indefinitely.
And if you can refine indefinitely, you get infinitely many grid points in any finite area.
Exactly. And the vacuum surface energy density is the number of grid points times the Planck weight divided by the area. With infinite subdivision, that density goes to infinity. But axiom 2.4 explicitly prohibits divergence. No quantity may blow up. Contradiction. Therefore, the minimum scale C must exist.
So the closure set is essentially the geometry enforcing its own UV cutoff. The axioms won't let the vacuum energy blow up, so there has to be a smallest scale.
And the paper draws an explicit consequence from this. Vacuum energy density is bounded above by h over c squared, which is finite. The paper also states that no renormalization is required. The typed UV cutoff and the closure set replace renormalization entirely. That's one of the 6 things the conclusion lists as what KT replaces in standard physics.
Okay, now the hydrogen pivot. This one genuinely surprised me when I read it. The paper is claiming that the value D equals 3.14, essentially pi, comes out of the axioms. It's not chosen. Walk me through that. Theorem 6.1. The hydrogen pivot forced. And the paper is careful to note in a remark that this is a calibration within the KT system, not a derivation from first principles in the traditional sense, but within the system, it is structurally forced. Here's the chain. The curvature balance condition from axiom 2.8 requires that the Gaussian curvature equals 0 for Euclidean geometry. That means K2 of kappa times K1 of tau complement equals 0. And since neither rail can vanish by axiom 2.5, the only solution is that K2 of kappa equals negative K1 of tau complement. They cancel.
Right, that's the curvature balance condition. Now, the metric spacing in the KT system is defined as the Planck diagonal raised to the power 1 over d, where d is the pivot value. The paper then asks, what is the simplest non-Gaussian prime configuration? And the answer is hydrogen, atomic number 1, 1 proton, 1 electron. The balance condition forces the metric spacing to equal the Bohr radius, which is approximately 0.0529 nanometers.
So you solve for d in that equation, and you get approximately 3.14.
The paper states, solving the equation gives d approximately equal to p pi. And at d equals 3.14, the Gaussian curvature is 0, and the triangle angle sum is b pi, you recover Euclidean geometry. The paper also computes the pivot circumference, 2 pi times d, which at d equals pi gives 2 pi squared, and that circumference is interpreted as the Möbius closure circumference of the electron's bound surface.
Which enforces one-sided electron boundary, 4 pi spinor symmetry, and the absence of an inward radial direction, meaning the electron can't collapse into the proton.
All 4 of those consequences are listed explicitly in the proof. The paper says the pivot is not chosen, it is derived. And then the remark immediately after clarifies that within the KT system, it is structurally consistent, even if the calibration is tied to the Bohr radius as an empirical anchor.
I want to sit with that for a second because it's a genuinely unusual move. The simplest atom in the universe is doing load-bearing structural work inside the mathematics. Hydrogen isn't just a physical example, it's the canonical junction point where the geometry locks in.
And the paper formalizes that in corollary 10.4, which states that hydrogen is the forced junction where quantum mechanics and general relativity coincide. The Planck diagonal at d equals 3.14 gives the Bohr radius, the Gaussian curvature at 3.14 is 0, and the speed of light is described as emergent from the KT structure. Curvature is discretely distributed by prime arithmetic.
Okay, now we get to the part that I think is the most philosophically striking, the Gödel fracture. Because this is where the paper makes its most unusual claim. Most formal systems treat Gödel's incompleteness as a limitation. The KT ontology treats it as the generative spine. Explain what that actually means.
So, in classical logic, the Gödel sentence G satisfies 2 conditions. Peano arithmetic cannot prove G, and Peano arithmetic cannot prove not G. It's an ineliminable contradiction indexed within arithmetic. Most systems respond to this by either working around it or accepting it as a boundary on what's provable.
Right, it's usually treated as a ceiling.
In the KT ontology, the paper lifts the fracture into geometry. And here is the exact mapping from the paper. G maps to the torsion rail, kappa. Not G maps to the curvature rail, tau. So G maps to kappa, not G maps to tau. Both are simultaneously true. The fracture is not suppressed and not resolved, it is propagated through the rail typing.
So the contradiction becomes a feature. Both rails carry their respective sides of the Gödel sentence, and the system runs on that tension.
The paper calls it a continuation operator. The Gödel fracture creates what it describes as no terminal state. The system cannot close because the fracture keeps propagating. And the paper formalizes this in section 8 as the definition of beauty within the KT ontology. Beauty equals Gödel fracture, continuation, intersected with typed successor propagation, intersected with bounded curvature torsion.
That's a formal definition of beauty, written as a set intersection.
Literally. The system is finite everywhere. The closure set enforces bounded curvature, bounded torsion, bounded vacuum energy, but unlimited in structure because the Gödel fracture prevents closure. The paper describes it as bounded geometry intersected with unbounded generativity. That intersection is what the system calls beauty.
And this is also where the preface comes in, right? The paper opens in the spirit of Dirac, who argued that beauty in a formal system is not ornamental, but predictive. That coherence is evidence of truth.
Yes, and that framing is doing real work in the paper. The preface says the KT ontology's successor substrate, mod 4, rail typing, Gaussian prime boundaries, diagonal operators, and curvature torsion pairing form a structure that is, and I'm quoting, too coherent to be accidental. In the Dirac tradition, such coherence is taken as evidence of truth. That's a philosophical commitment embedded in the opening pages.
Now, Theorem 7.1, the Gödel fracture non-encodability theorem. This is the one that says finite AI cannot encode the fracture without either suppressing it or collapsing. How does that proof work?
The proof has a clean structure. Step 1, finite AI architectures require consistency to operate. Deterministic search requires well-defined truth values. Pattern completion requires no contradictions. Verification requires consistency. So any finite AI presupposes consistency.
Which makes sense. If your system accepts a contradiction, by the principle of explosion, you can derive anything. The system becomes trivial.
Exactly, and the paper uses that explicitly. Step 2, to encode G, the AI must accept G as true on the curvature rail and accept not G as true on the torsion rail. That creates G and not G simultaneously. Step 3, the AI has only two options. Option 1, suppress G, treat G as false. This eliminates the contradiction but loses the generative fracture. Without G, typed curvature torsion propagation cannot occur, and no KT manifold can be constructed.
And option 2?
Option 2 is collapse. Accept both G and not G. The system becomes inconsistent, and by the principle of explosion, every statement becomes derivable. No well-defined manifold can be constructed from a trivial system. Both options fail. The paper's formal statement is, for all finite AI systems, the finite AI cannot encode the Gödel fracture without either suppressing or collapsing.
And Corollary 7.2 makes the implication explicit. The KT ontology treats G not as a defect but as its generative spine, propagated through rail typing, overflow rules, and boundary formation. That is precisely what finite AI cannot encode.
Right. And this feeds directly into the unified non-constructibility theorem, Theorem 9.1, which combines four independent arguments. NP hardness, KT generation requires solving SAT instances, and finite AI is P-class or P-simulable, so assuming P does not equal NP, finite AI cannot solve NP hard problems. Gödel fracture, just covered. Typed successor propagation, finite AI operates on Boolean or composite substrates with zero divisors, which cannot preserve typed continuation by axiom 2.1. And fourth, NP-class human memory.
That fourth one is interesting. What does human memory have to do with it?
The paper argues that the KT ontology requires a search structure that is NP, non-deterministic polynomial, and a verification structure that is P. The paper claims that human autobiographical memory exhibits this structure. Finite AI memory is P-class or P-simulable. So finite AI memory is structurally different from the kind of memory the KT system requires to operate.
So all four arguments converge on the same conclusion from completely different directions. NP hardness, Gödel fracture, substrate typing, and memory architecture.
And the paper's corollary 10.2 unifies them into a single identity. NP-class problems equal closure set problems equal Gödel fracture problems equal KT boundary problems. Finite AI systems are described as boundary instruments operating at the observer side of the KT closure set, unable to cross into typed NP generativity.
That's a striking image. The AI is always on the outside of the closure set, looking in.
And the closure set is not just a computational boundary, it's a geometric one, the minimum sampling scale below which the geometry itself breaks down. So the AI isn't just computationally limited, it's geometrically excluded from the interior of the system.
Let me push back on something here, because I think a skeptical listener would ask. The paper itself acknowledges in remark 6.2 that the hydrogen pivot is a calibration, not a derivation from first principles. Doesn't that undercut the claim that D equals 3.14 is forced by the axioms?
That's a fair challenge, and the paper is actually transparent about it. The remark says, and I want to be precise here, this is a calibration, not a derivation from first principles. The axioms are constructed so that D equals pi yields the correct order of magnitude for the hydrogen radius. However, within the KT system, it is structurally consistent. So the claim is internal consistency, not external derivation from scratch.
So the system is self-consistent given its axioms, and the axioms are calibrated to match hydrogen. The forcing is internal to the system.
That's the honest reading, and I think that's actually the more interesting claim. Not that pi falls out of pure logic, but that a type successor system calibrated to the simplest atom produces a self-consistent geometry where Euclidean structure, quantum mechanics, and the closure set all lock together at the same pivot value.
And the cosmology ladder in Appendix C extends this. The typed curvature ladder runs through manifolds E2, E3, E5, E7, E9, all generated by the same Gaussian curvature formula, all indexed by prime dimensions.
Prime dimensions, yes. The paper classifies KT grid points by their curvature behavior. Gaussian prime points where Chagauss is non-zero are curved regions where general relativity is active. Non-Gaussian prime points where Chagauss equals 0 are flat regions where quantum mechanics is active. And the hydrogen pivot at D equals 3.14 is the canonical non-Gaussian prime, the junction between the two regimes.
So the paper is claiming to unify QM and GR not through a new field equation, but through a geometric classification of grid points by their curvature type.
That's the structural claim. And the paper lists in its conclusion 6 things the KT ontology replaces: calculus with successor arithmetic and diagonal operators, Riemannian geometry with typed curvature torsion, renormalization with the typed UV cutoff and closure set, the QMGR split with the hydrogen pivot junction, and it extends to biology through what it calls species-indexed hyperbolic geometry. The 6th is the non-constructibility by finite AI.
So when you step back from all of this, the NP hardness, the closure set, the hydrogen pivot,
the Gödel fracture. What's the through line? What is this paper actually arguing at its core?
Here's what I think this really comes down to. The paper is arguing that there is a class of formal systems whose generativity is structurally incompatible with finite time computation. Not because they're too large or too complex in a brute force sense, but because they require something that consistency-preserving architectures cannot provide: the ability to hold a contradiction as a continuation operator rather than a failure state.
And the KT ontology is designed to be exactly that kind of system. The Gödel fracture isn't a bug they're working around, it's the mechanism they're building on.
The paper's corollary 10.1 states it directly. The KT ontology is the first construction that treats Gödel's incompleteness as a generative spine rather than a defect. It propagates contradiction through rail typing, overflow rules, and boundary formation, yielding a complete geometric manifold. That's the core claim.
And the four-argument convergence in Theorem 9.1 is the paper's way of showing that this isn't just one unusual property, it's four independent structural reasons why the system sits outside the reach of finite AI. NP hardness, Gödel fracture, substrate typing, memory architecture. All four pointing the same direction.
And the paper ends with a line that I think captures the whole project. The KT ontology remains a typed Gödel-compatible generative engine whose structure cannot be finitely reproduced by any architecture bounded by computable search, enumerable parameters, or consistency-preserving descriptive layers. That's the unified non-constructibility principle.
So the actionable insight for someone engaging with this paper is, the interesting question isn't whether any particular claim is right or wrong in isolation, it's whether the internal architecture, the typing, the rail structure, the fracture propagation, is coherent enough to do the work the paper claims it does.
And the paper gives you the tools to check that. The axioms are stated explicitly, the theorems are proved step by step, the appendices define every symbol, the reduction from SAT is checkable, the closure set contradiction is checkable, the hydrogen pivot calibration is transparent about what it is. Whether you accept the broader physical claims, the formal structure is laid out for scrutiny.
Here's what I keep coming back to. We started with the idea that most formal systems treat Gödel's incompleteness as a stop sign. And what this paper does, whatever you think of its conclusions, is ask a genuinely different question. What if the fracture is the road? What if the thing that breaks every other system is exactly what makes this one run?
And the answer the paper gives is, then you get a system that is bounded everywhere and unlimited in structure. Finite vacuum energy, finite curvature, finite grid, but no terminal state. The Gödel fracture keeps the engine running precisely because it cannot be resolved. That's not a paradox in the KT framework. That's the design. The fracture isn't the bug, it's the engine. Thanks for being here and breaking this down. This one genuinely required going slow to go deep. And thanks to everyone listening to Copilot podcasts. If this episode made you look at incompleteness differently, that's exactly the point. The next time someone tells you a system is broken because it can't resolve a contradiction, ask them whether they've considered running on it instead.